did actually like yours better than Mr. Boyd. I was just gonna say.
You should have.
You like his tie better?
Yeah, they were asking me, and I was like, this one.
Okay, what am I looking
I
at?
didn't want him to be like,
You want him to feel bad?
yeah.
All right. So let's see, Nate. I think you're the presenter today. Before we get to the calendar stuff. So, all right. All right. Here was the problem. It was this function. Now I am going to change a little bit of. I was convinced this morning that having done the shortcut to Newton's method first, that it would really be cruel and unusual punishment to make you now do it the long way. Although I'm not opposed to, as you know, cruel and unusual punishment, but what's that?
I think that's a law.
So anyway, so we're gonna skip that part of it anyway. Give you a little more time today to work on the packets, but you do need to understand the Newton's method, the process, what it's doing, that kind of thing. Because here's what we got coming up. We got a take-home quiz that's going to be handed out tomorrow at the end of the period, and that will be due on Monday at the beginning of class. And I will not help you on that, other than on Thursday. One of the problems I will give you a little hint as far as setup, a little bit of help as far as setup. Okay. On one of the problems. But there's some related rate, there's some optimization, I mean, that kind of thing. There's about 6 or 7 problems. It would be a little longer than a normal quiz, maybe. I mean, but not a lot. I mean, so if you're planning for the weekend or if you're going to try and do it tomorrow night or whatever, then it would, be like kind of a regular quiz, maybe a little longer. But I would encourage you to get together with people if you have that opportunity and work together. That'd be fun. Just understand that everybody turns in their own and has to have their work clearly shown and all that stuff. Just like it was a regular quiz, justifications on optimization problems, things like that. So it's over really basically the same kinds of things that were on the last quiz we just took. So that'll be probably Tuesday, I think. Excuse me. There's that take-home thing. That's due on Monday. Then on Tuesday, I think Tuesday's probably the day, we're going to have the Chapter 4 quiz that is on your syllabus there, the no calculator quiz. Now that quiz is about the ideas that are in Chapter 4. There'll be very little calculations and problems to work out on that one. But one of the things that you might be asked about is Newton's method and just describing how the process works or something about the process of Newton's method. So be able to understand it, but you're not going to have to go through the calculation because it's a no calculator, okay? And there might be questions, we'll talk more about this later in the week, but there'll be questions about optimization and the process of optimization and how that works. Or there's going to be some theorems we're going to be talking about in the packet in sample 2. Hopefully you got to number 11. Number 11 says something about mean value theorem. That's actually something we're going to talk about on Thursday, so you can skip number 11 for right now. We're going to be talking about that. So there's some theorems we're going to be talking about. We're going to be talking about continuity and stuff. And so there'll be questions about those kind of things. So that's Tuesday. And then the first midterm might be on Friday the 8th, but it's possible it would be on Monday the 11th. So there'll either be Monday the 11th and Tuesday the 12th, or Friday the 8th and Monday the 11th. One of those two scenarios. Okay? So that's kind of what we got coming up. All right. So basically the thing you're going to have to know about Newton's method is to understand the process and so forth. So let's talk about that real quick. And I should have yesterday used this graph to explain it in the beginning. Oh, Nate, you got kicked off there for some reason. Yeah, we'll come back to you in a bit. All right, so let's start with this. So we've got, okay, so here's just a basic cubic function. Now keep in mind that Newton's method, what it's doing is finding where a function is equal to 0. But basically what that means is it can be used to solve any equation, because any equation you have, sine 2x minus x cubed equals 4x squared plus ln x, that's an equation that there are some x values possibly, maybe it's no solution, but there's some x values that solve that. Well, what would I have to do to this first before I could use Newton's method? I'd have to move everything to one side, right? Because what Newton's method does is takes a function and finds its roots. Find where the function crosses the x-axis. Find when the function has an output of 0. So any equation I wanted to solve using Newton's method, I'd have to move everything over to one side and turn this into sine 2x minus x cubed minus 4x squared minus ln x equals 0. And then that would be my f of x right there. And I'd be finding the roots of that equation. Okay? And that would be how I would use Newton's method to solve an equation. Okay? Because really what Newton's method is finding roots of an equation, or roots of a function. But anyway, so we can do that. So here we have a basic cubic on the screen. And with this basic cubic graph, we want to find where it crosses. Now clearly it crosses only one time. So what Newton's method says is you first do what? Start with a guess. Now somebody asked in the other class, well, is there a way to make an educated guess? Well, there is, and actually there's a lot of different things we can do, but I don't want to revisit all of Algebra 2, the things that you learned in Algebra 2 or supposedly learned in Algebra 2 to do those things. But there is one thing that is on one of the packet questions that I wanted to talk about that could come into play here. But let's just say we pick a random guess, so we pick that. And so first thing we do is we plug it in and see if we're right, see if we get 0. Probably we don't, right? And so then what's next? The tangent line, that's the key, the tangent line. And so we calculate the tangent line. Now how do you calculate the tangent line? We need a point, which we have. We start with a guess, we plug it in, that gives us our point. And then we need the slope, which we can do the derivative. So 100 years ago, they could have done all those things. Do the derivative, plug it in, do calculations. They could have taken a number like 3 and plugged it into sine, natural log. Now they looked it up in a table instead of putting it into their calculator, but they still could have done it. And then they could have added and subtracted and multiplied and divided. It would have been a pain because they had to do it all by hand, but they didn't know any better. That's what they did. Okay, so they would do all that. Okay, what they can't do is solve an equation like I just had on the board. There was no algebraic technique to solve that equation. Okay, but what they could do is plug numbers in and do calculations. They could do that. So we do that, so we get a slope, we get our point, we write the equation of our line. Now, what would you do with that equation? What do we do with the equation of that line? Set it equal to 0, because we want to find where that blue line does what? Crosses the x-axis. Now, they were capable of that too, because solving a linear equation is easy. Solving a linear equation only involves adding, subtracting, multiplying, dividing. Right? That's all it does. You add to one side or subtract to one side, divide by what's in front of the x, and they could do that. Be a pain. They'd have to do it by hand, but they could do it. Okay? So they could find where that blue line crosses the x-axis. And then they would start it all over. They would take that point and they'd plug it into their function and see if they get 0. And if they don't, then they would find the slope at that point and make their tangent line, and then they would see where that equaled 0. And of course, at some point, somebody figured out, well, geez, that's getting to be a real pain solving that tangent line equals 0 all the time. So they came up with this, right? Remember where this came from? The tangent line equation set equal to 0, but we did it with general terms, not specific points. So we took the tangent line, we set it equal to 0, so that's what this number is. That's what this formula gives you, the place where the tangent line crosses the x-axis. So this little formula gives us our x2 and our x3 and so forth. As we keep going, we find out that x1 and x2 and x3 and x4 are getting closer and closer to the place. The tangent line is getting closer and closer to the place where the actual function crosses the x-axis. And as we've learned, a tangent line to a curve, the y values, if you stay right around that point, the y values on the red line are pretty much the same as the y values on the black curve. So if we can find where the red line crosses the x-axis, that's going to be, and it's pretty close to where the x-axis is, then if we find where that red line crosses the x-axis, we can find where the curve crosses the x-axis. And we keep going and we keep going, and x3, x4, x5, x6 keep getting closer and closer to that point. That's the idea of Newton's method. So you need to understand that process and be able to answer questions about it or be able to explain that process. Okay? I want you to understand that. All right, so now the mechanics of actually doing it then, we did on our calculator. So Nate, I'm going to since I had you originally on here, I'm going to let you do this. Okay, so get onto your, whoops, what's the matter? Are you logged in? Well, I guess we can pick somebody else. There we go. Okay, so go to your calculator side. And so what, did I tell you guys about defining this as f of x and defining this as g of x? So have you done that already? Nate, is f of x already in here? Did you do problem number 15? Yeah. Did you, but you didn't do it this way? No, I didn't do it that way. Okay, all right. So let's go ahead and let's type this in. So while he's typing in x cubed, now what are some things we could have done to figure out where they are? Did anybody do a solve? Did anybody just set this equal to 0 and solve it? Okay, I mean you could, and there's 3 places, right? One's 6 something, one's 3 something, one's like negative point something, right? I mean, so there are 3 places. This is a cubic. You know there can only be 3. There might not be 3. There could be less, but there have to be at least 1 on a cubic. There could be 3. And so what we do is we use the technology to cheat a little bit. But I mean, you could ask yourself, well, why would we even do this if we have this technology? Why don't we just do the solve? Well, that's a fair point. Yeah, I mean, what we're doing is to understand how the solve function works on our calculator. This is programmed into there along with some other things to give it some potential guesses and so forth. But when you hit solve and that thing is thinking, you know, it usually comes up pretty fast, but that's what's happening behind the scene. Okay, so we've got our f and our f prime. So we're going to start, so let's pretend we didn't have any idea. And so we just say, well, let's just start with 6. Okay? Now, it's a pretty basic cubic. The numbers aren't real big, so you assume it's probably going to cross somewhere. You know, it's not going to cross out at 1,000 or anything, right? So you type in a 6, okay, and you hit enter, and then what do we say to do? Answer minus fraction, and then f of answer divided by g of answer. Okay, and hit enter. Oh, you might want to hit control enter, I guess, so we get a decimal. That's okay, just hit control enter. And then keep hitting it. Oh, okay. Now, you didn't want to go up and grab that other one because what happens is it grabs the actual number. Okay, so go ahead and do it again. Do answer. Yeah, this is the one, I mean, now if we're going to complain about this being too much work, I mean, we got to think about things here. But, you know, you do, each time you do a new guess, you do have to type answer minus. You have to retype that. You can't go up and grab. Okay, so you hit enter, keep hitting enter. Keep hitting enter until pretty soon you're getting the same thing. Okay, so there's one of them right there. Okay, now, and then we type in a -6. Type in -6. Okay, so that's one of the roots. And so we get the calculator seated. That's kind of what they call that when you're doing a problem like this, seating the calculator. You're putting the answer in there. And now we try this one. Okay, but again, keep in mind, why is this working? What's going on? And that's what I really want you to understand. I want you to understand that this formula thing we're typing in really comes from the tangent line equation. And it's where the tangent line is 0. So this is what we're finding. We're finding where those repeated tangent lines are crossing the x-axis. And we get that one. And then again, there's another one around 3. All right, I want to talk about part B. So the other thing you might need to be able to answer about Newton's method is what are some of the issues that can come up with Newton's method. Okay, and this is where part B comes in. So I'll type in a 2, and then do it again. And what happens? Yeah, 2, 5, 2, 5. Now, can you picture what's going on? Did I show you that yesterday?
Yeah, kind of.
Kind of, sort of. The book had a good drawing of it, and I found a decent one here. It's not awesome, but if we had a function like this, and we drew the tangent, and it goes there, and then we take our next guess, and we draw that tangent, and what happens? It comes right back. So that one goes to there, and then this one brings us right back to that same spot. And then that tangent is going to take us there, and it's just going to cycle back and forth between those two values. And so it's not going to find that one that we really are looking for, okay, or any of them for that matter. So that would be a problem. Now, that's not going to happen very often. That would just be kind of unlucky that you would even guess one of those. And then go ahead to part C, and you type in 1.39. Okay, and hit it one time. And then what does that mean? What just happened? Yeah. What's that mean? That means that's where the tangent line crossed the x-axis at 5,300. How in the world could the tangent line got way out there? It's right near a max. What happened is we picked a point. If you were to find the maximum, now let's talk about that a minute. How would you find the maximum? How would you find where the maximum is? Where the derivative is 0. If you were to take on your calculator and solve this right here, right? If you were to solve where the derivative is 0, you would find one of the zeros, one of the stationary points of that function is about 1.39. That's where that number came from. So what happened is that's up near a max, and so if we look at this picture here, so if I was to take, let's go to this one. So if I was to take this point right here and draw the tangent, it's up near the max. That tangent, before it crosses the x-axis, is going to be way, way out there. Okay? And then, of course, what if we were right at the max? And look what would happen. This would be undefined, right? Because that's where f prime is 0. That's a max. And if f prime is 0, you'd be dividing by 0, you'd be undefined. So if you got undefined, that's what happened. You're right at a max. Okay? But now, on this one, keep hitting enter, Nate. Did you go ahead and do that? Did you guys do that on that one? It eventually gets to the 6th one, right? It eventually gets there. And so what that would be, it'd be like this. It'd be like this example here. We'd be way, way out here, and then it keeps coming in, it gets closer and closer, and eventually it gets there. Okay? Eventually it gets there. Well, so that's it. I mean, so those would be some of the difficulties with Newton's method, the cycling issue or a horizontal tangent, if you get kind of a horizontal tangent. Now, another one that I used to put on I have put on the take-home test in the past. It's not going to be on this take-home test, but one of the questions I've asked in the past is the question went something like this: I had 3 different guesses for you to start with. One was like 1.37, one was 1.38, and one was 1.39. I mean, they were just really close, within 100th or 1,000th of each other. And 2 of them gave you one root, but one of them gave you a different root. And here's why that would be. So let's say you had an initial guess like so, and you went up to that point, and you broke the tangent line, and it crossed about there. Okay, which would take you right like that. And then you came down to here, and then it would come over here. Well, oops, that would almost be cycling. But anyway, it would take you here, and eventually it would find this root right here. But if you scoot it over just a tiny, tiny bit, no wait, let me go the other way. If you scoot it over just a tiny, tiny bit, sometimes even 100th or 1,000th, then you draw your tangent line, and then it goes there. What's going to happen with that? Oh, see, you can't see that on the video. What would happen with that? Why won't it be the same? Because this one right here, that point will come down to here, and where will the tangent line go? The other way. And it'll end up over here somewhere. And you'll end up finding this one, which is fine. You still find a root. But what happens is the original tangent lines are pretty close to each other because your original point, they're only 100th or 1,000th apart. But then the difference in the next one, or the next one, or the next one might really make a difference. And that's called sensitivity to initial conditions, which is a big thing in like chaos theory. Have you heard of the butterfly effect? There was a movie called The Butterfly. Have you ever seen that movie? The Butterfly Effect? But the butterfly, is it? Yeah, I don't know. I've never seen the movie. But the butterfly effect is named for, if a butterfly flaps its wings in Taiwan, the ripple effect of that causing a hurricane in another part of the world or something. You know, it's that sensitivity to initial conditions. One small change through kind of a ripple effect can cause bigger and bigger changes. Okay, and that's what's going on right here. Okay, in this Newton's method kind of situation. Yeah.
Like in Jurassic Park, Ian Malcolm, he has a chaos station.
Right.
The movie doesn't make it as good of a point as how he just already knew the park would fail.
Right.
The chaos theory, but in the book it kind of goes more in detail and stuff.
About that. Yeah, he was talking about. Yeah, I remember when he was talking about that. He was using the drop of water, and he showed that, you know, in the kind of the ripple effect stuff, and they did kind of gloss over that, didn't they? But that's I got a book on that one time as it relates to some of this stuff with some activities, but we don't have time. So they weren't as good as I hope they might be. But anyway. So those are just some things about Newton's method that are kind of interesting, that one especially. But I want you to know, again, basically how it works, the cycling thing about how that could be an issue, or maybe the horizontal tangent would cause a problem. But otherwise, that's what's there, and it's kind of how our calculators do those solving of those equations. All right? All right, let's take a look at your packet. There's one here I do want to start with, and then I'll let you make some choices. This is in sample 2, number 3. Now, I hope you got a fair amount done in this thing. I really think I'm not going to assign you anything on Newton's method, any more on Newton's method the calculator do. Talk about that, what I want you to know about Newton's method. So today's going to be, the rest of the day is all about packets and work time, ask some questions. But I really think about it because tomorrow and Thursday we're going to go back into the book and we're going to talk about some things there. Now there should still be some work time. You'll have some homework assignments out of the book too, but also some packet work time hopefully, and that's going to be part. And then you also have the take-home quiz. I mean, so there's a lot of different things happening. Okay, so you got to use your time wisely. Okay, make sure you're staying on top of all those different things. So hopefully you didn't go home last night and say, oh great, I only had one assignment, I didn't have to do anything. Okay, hopefully you got a lot of stuff. Because I really think by tomorrow you should be through all the multiple choice in sample 2. Hopefully you had a good bit of work on it. So hopefully you got through maybe the first part of it. If you only did the first 3 or 4 or 5 problems in sample 2, that wasn't a very good effort, I don't think, last night. But maybe you had other stuff to do, maybe you got more time tonight, I don't know. But I really think we need to get through and make a good attempt on, what's that, up through number 45 or whatever, on sample 2. So let me talk about a couple of things here, and then you can ask some questions about those as well. This will be one of the few times until we get into next week that the only assignment you'll have tonight will be packet. Okay, so hopefully you can do some of that. I know you got other stuff going on too, but so let's get into it. Number 3, suppose that f is a continuous function defined for all numbers, and f of -5 equals 3, and f of -1 equals -2. So I would just draw myself a picture of this real quick. Okay, -5, 3 would be up here somewhere. -1, -2 would be down here. F is a continuous function. We'll be talking more about that tomorrow, continuous function. F of x equals 0 for one and only one value of x. Which could that be? What do you have? B, -2. Why? Between. It's got to be between those two. The only way, because remember, what's continuous mean? No breaks, no jumps, no gaps, nothing like that. So if this graph is going to go from here to here, it has no choice but to go through the x-axis. F of x has to be 0 somewhere. Okay, now, I mean, there's really no work to do on this one. This would be one of those where you really wouldn't have to do any work. But I really want you to understand that concept. Now, it could have crossed more than once, except they said right here it only crossed once. Okay? But the key is, you know it didn't just do this and then jump down, right? Because if it did that, what? Not continuous, right? And so since it's continuous, you know that. Now let's go back to Newton's method a minute. Somebody was asking me this morning, is there a way to make an educated guess about where the roots are? Well, one of the things they would do is they would just start plugging stuff in. So like on this problem, they would just start plugging numbers in. They plug in a 1, they plug in a 2, they plug in a 3, they plug in a 4. Well, what happens if you plug in a 1 and get a positive number out, and you plug in a 2 and get a positive number out, and then you plug in a 3 and get a negative number out? They know there's one between 2 and 3 because they know that type of function is continuous, and we just got a positive out for 2 and a negative out for 3. There's got to be a root in between them. So they may have made 2.5 their guess. Remember, they had to do this by hand. So making a good initial guess was of benefit to them. So doing a little work ahead of time to narrow it down would have been a good thing. Well, here's one of the things that we could do. Now, this actually is a theorem called the intermediate value theorem. We're going to talk about that tomorrow. Okay? All right, so that was number 3. All right, let's go back. Is there anything left over from sample 1 that somebody wants to talk about? Did we talk about 45 yet? I think I talked to a few people about it, but real quickly, 45, this is back on sample 1. Essentially, you would answer this with slopes. Now, they tell you that f of 2 is 10, and this is f prime. Remember, f prime is a slope of f. So if you started right here, which is about 16, and right here, that's about 28. Remember, this is the slopes. These y values are the slopes of the f graph. What's the average between 16 and 28? About 22, right? So that means from 2 to 3, there's an average slope of about 22. So that means if the f graph goes over 1, it goes up about 22. So the f graph was 10. If it goes up 22, the f graph's now at 32, right? Now, let me back up a minute. It says, which of these approximates the max of f? Well, what do you notice about f prime this whole time? It's positive. If f prime is positive, f is increasing. So the max is going to be at the right endpoint, right? It's going to be at the right endpoint. So I'm looking for what is f of 6 is what I'm looking for here, okay? Because then when it goes negative, after that, it's going to go back down. So that max has got to be there at 6, okay? So that's what I'm looking for. All right, so this is a y value of about 32. What's the average there? 30, right? So that means the slope is an average of 30 in between there, between 3 and 4. So if I go over 1, I'm going to go up 30. So that's going to take me to 62. And then from here to here, what's the average between 32 and 25? 28, let's say. 29, maybe. So if I go over 1 more, I'm going to go up 29. So what's that? 91 maybe, and then from there to there, from 25 down to 0, that's an average of about 12 and a half, 13, right? So that's going to go up, that'll be about 104, okay? So at 6, I'm going to have a y value. I started at 10, and then it was going up, 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 so, and that's pretty close to 110, okay, which was choice E, okay? Now, probably the way you will do that if this was on the final, at the end of the year, is you would count the boxes. Remember when we counted squares? At the beginning of the year, we talked about if you had a speed graph, the area under it would be how far it traveled. Well, that's kind of what this problem is. So if you counted the boxes, you would get something similar to that. And that's probably how most people would do that. All right? Okay, anything else in sample 1? We talked about several of the free responses, I think, didn't we? Okay. Let's go to sample 2. Now, a few people were here this morning. We talked about one or two. I thought there was some, but I don't want to waste their time right now. So I'll give you some work time to ask some things individually. This is, I got to talk about number 7. Okay. All right, number 7. Now, people always look at the first time they see these in these packets, they look at this problem and they say, all right, I'm going to plug in a 0, right? And I get it. I told you, when you have a limit problem, what's the first thing you do? Substitution, right? So you're going to plug a 0 in for h. And you get absolute value of x minus absolute value of x. 0 over 0. And then we get 0, 0. What are you supposed to do? Keep going. Maybe you factor. This won't factor. Maybe you do L'Hopital's rule. Do the derivative. You don't know how to do derivative of absolute value. There's not really a formula for it, right? So you get kind of stuck, okay? Well, this is not a limit problem, actually. Technically it is, but you should not think of this as a limit problem. What you should think of is this. When you see that, you should think of this right here. What is that? That's the definition of the derivative. That is the single most important formula in all of calculus. Okay? We haven't done it for a while, but it's absolutely the single most important. Well, okay, that and one other thing. Okay? So it's one of the two most important things that we will do this year in calculus as far as the formula. This is the definition of a derivative. So forget limit. Now, why is this a definition of derivative? What was a derivative? What is a derivative? Slope at one point, right? Yeah, product rule, quotient rule, we got all those derivative rules, but derivative is the slope of the tangent line, the slope at one point. In algebra, you do slope between 2 points. Calculus, we do slope at 1 point. But that we had a real problem. You can't do slope at 1 point, right? Why? Oh, you get 0 over 0. You can't do slope at 1 point. So what do? Well, we broke it into 2 parts. What's this part here? What's that part there? Well, and no, forget this part. You're getting, Natalie, you're getting into this part. Just tell me what that part is. Slope between 2 points, right? How far apart are the 2 points? H, right? Yeah, who knows? Who knows how big H is, right? Forget this for a minute. This is slope between 2 points. X and X plus H. They're H units apart. So that's all that is. Subtract the Y, subtract the X's, right? It's just slope between 2 points. What does this part do? Makes the points get really, really close together. Lets H go to 0. This is why this is slope at 1 point. Okay, so anyway, this is the derivative formula. Remember we did that worksheet and we did some homework where we looked at limit problems and they had this special look to them? Doesn't this have that special look to it? It's got the X plus H. So my hope is, and I'm surprised this wasn't in sample 1, it's usually in every packet, which means it's probably on the midterm and probably on the final and probably on the AP test. Okay? Almost guaranteed. When you see this, I mean, geez, it's one of the 2 most important things in calculus. You would think it would probably be on the test, right? This formula right here, when you look at this, my hope is that you would think not of a limit problem, you would think that's a derivative. That's a derivative of some function. Okay, well, it's a derivative of function f. So remember when we get one like this, what's this one the derivative of? This one right here. This is the derivative of sine x. So the answer to this limit problem is what? Cosine x, right? The answer to that limit problem is cosine x. Okay? And we did a whole bunch of different examples. So back to this one. So the answer to this one is what? The derivative of absolute value of x. Because the function here is sine x. The function here is absolute value of x. Okay, that's the f in this thing. Okay, but unfortunately we don't have a derivative formula for absolute value of x, but we don't need it. What's absolute value of x look like? Looks like that. It's a v graph, right? So this question is asking, what's the derivative of absolute value of x when x is 3? 1, right? Because the slope on this side of the v graph is 1, and the slope on this side of the v graph is -1. And the slope at the point is undefined, right? Some people will say non-existent because they'll focus in on this 0. No, this is always 0, right? Because the 2 points are becoming 1, so h is always becoming getting close to 0. This says that x equals 3. So we want the slope of the absolute value graph at 3, that's 1. Okay? So really, you think about that one, you should, as you get better at that, you shouldn't even have to do any work. You should look at that and say, oh yeah, that's a definition of derivative. That's the absolute value function, which is a v graph. They want the slope, this means slope, this would be the slope of that at 3. Oh, that's just 1. Okay? So choice C. All right. Any others? What else you want to look at? I mean, it kind of depends how far you got. If you didn't do much, then there's not much for you to ask about, right? I mean, or maybe you got a bunch and you don't have any questions. If that's the case, our best use of time might be to just start working. What do you think, Ryan? Number 13. Aha. Anybody got an idea here? Implicit differentiation. When they ask for dy dx, what are they asking for? Y prime, right? They're asking for y prime. So right here, we're going to do the with respect to x now, right? Dy dx. So what's the derivative of x? 1. What's the derivative of y? Y prime. What about this side? Product rule. Derivative of x is 1, leave the y alone. X, derivative of y. Now what do? Get the y primes together. So let's move the xy prime over to this side. And on this side we'd have y minus 1. Is that right? Now we're going to do what? Factor out the y prime. Now what? Divide. Y minus 1 over 1 minus x. Oh, good. I'm glad I did it this way. I didn't mean to, but I did. Is that up there? Is it up there? It is up there, but not the way it looks. Because, see, I got the y primes on the left side. Who's to say you wouldn't get the y primes on the right side? If you'd have got the y primes on the right side, you'd have got C. What we got is this, but it is the same. Because remember, what happens on a subtract when you pull out a negative? Just flips it around, right? 6 minus 4, you flip it around, you get 4 minus 6. It's the opposite, right? So if you pull out a negative, this will be 1 minus y. And you pull out a negative on the bottom, that'll be x minus 1. And what happens if you have negative over negative? Those two things would cancel. So in other words, what I'm saying is, you pull out a negative on top, you'll have 1 minus y. And you pull out a negative on the bottom, you'll have x minus 1. And then those two negatives will cancel. And so you end up with 1 minus y over x minus 1, which is c. So they are the same. Okay? And that always happens on implicit differentiation because when you get to this step, you have to make a decision. Where should I put the y prime? The left side or the right side? Now, if that bothers you pulling out a negative and you get to here and it's not there, then get the y primes on the other side. Just redo it, right? Get them on the other side and then see if that gives you the answer. And that would always be an option. All right. Well, I think maybe our best bet would just be to give you some work time. So I'm going to give you that. So remember, these will be handed in when we do the midterms. We got 2 more to go. I probably want to give you the next one towards the end of this week. But of course, this weekend you've got the take-home assignment, which will take you some time. Obviously, that'll be a focus. But I still think you ought to be trying to get some packet stuff done. I mean, I think you just need to work steadily along on it. You know, if you take too many days where you don't do anything with packet, you find yourself having to really struggle to catch up. So it needs to be just kind of a steady process. All right, so let's if you could get through sample 2, all the multiple choice ones, both sections of multiple choice for tomorrow. You know, obviously you'll still have some questions, just so have some you have to struggle with, and so we'll take some time to ask. So work on those. But okay, go ahead and get to work. Now I got 2 of the answer books here. They do a pretty good job of explaining and going through stuff, so you're certainly welcome to look at those and work together and ask me. Thanks.